Hi everyone. This video covers section 1.3, which is on direction fields. So something we learned in the last section was a theorem about the existence and uniqueness of solutions to certain types of differential equations. But one weakness of that theorem is that while in some cases it tells us that a solution exists, it doesn't tell us anything about the nature of the solution. And so something that we can do to think about what does the solution look like is think about the nature of the differential equation in the first place. So if we consider a simple first order equation like I have written here, dy dx equals some function of x and y. Well, what is this saying? This dy dx, what does this represent? It's a derivative, and usually we think about this, I mean, it's really just defined exactly as the slope. So what this equation says is that at a particular point, x and y, the slope of the function y is the value of the function f. Okay, so that was probably really confusing. So what this is really saying, I guess, is at xy, the slope of the solution that we're finding. So the solution y of x, remember what we're looking for is the function y. The slope of y is f at xy. Okay, that's exactly what this is saying, because the slope of y of x is dy dx. Okay, so if we know something about the slope of a function at any particular point, then we can we know something about the shape of it, right? And so that's what we can do with what's called direction fields, is start looking at the shape of the solution. So here's an example. I've got my axis here, and what we're going to try to draw is y of x. But first we're going to draw the direction field so that we have some sort of shape. So remember the solution, there's no f in this problem anymore. Forget f. Our solution is y of x. It's some function y which depends on x. And so it makes sense to graph it on an xy axis just like this. So let's think about what the direction field is at a particular point. So let's say at 0, 0, dy dx, I'm going to plug in x equals 0 and y equals 0. So then the right-hand side is going to be 0. And if the slope of the function is 0, then that means that a tangent line to the curve would just be horizontal. And so I guess I'll use yellow. Our sort of at y equals, or at the point 0, 0, right at the origin, the direction of the curve would be horizontal. And in fact, really at any x didn't have anything to do with it. So at x comma 0, for any x, we have dy dx equals 0. So I can put more of these little horizontal lines all across the x-axis, right, at any point. I forgot to put in here my values, 1, 2, -1, etc. So let's think about a different point. Let's see, at, so again, x doesn't matter. So let's say any x, and then let's say y equals 1, then dy dx equals -2. So at the point 1, 1, my slope is going to be -2. So it's going to be a little bit, it's going to go from upper left to lower right, and it'll be a little bit steeper than 45 degrees. So kind of like that. Okay. When you're doing this in the homework, really, it just can't wait. It doesn't need to be perfect. And this is true for any x value, so I can sort of draw these parallel lines all like this. Now, what if I go up higher at x comma 2, then dy dx equals -4. So the lines start getting steeper and steeper. They're still negative direction, but they get sort of really steep. And pretty soon they'll be close to vertical. Like that. What about in the lower half of the graph? Well, that's pretty clear to see. At x comma -1, dy dx equals +2. Yeah, +2. So now our lines are going to go the other way, kind of like that, and they're the same all across. And at y equals -2, dy dx is +4. So now again, we've got really steep lines, but going in the positive direction. Okay. Now, what is our solution? This will do blue. So the solution really depends on where initial condition is, where some point on the graph is. Just like if you know the slope of a line, that tells you a lot about it, but you also need to know one point on it in order to know the exact formulation of it. Okay, like y equals mx plus b. N is the slope, but you also need to know the b where it crosses the y-axis. So let's say we know some point on it. Let's say we know that this point is on y of x. Well, now we know that up here, it's got to kind of look like this because it's got to have that slope. And then as it comes down here, as we come down here, we know that the slope is going to sort of start to mellow out and get shallower and shallower until finally, when we get down here, it's going to be flat. And we're not going to be able to cross the x-axis. So that gives us some notion of what the shape looks like. We could plot a different solution. Let's say we knew that we started over here. Well, then we know that right here we're going to be tangent to that line, and then we're going to start kind of mellowing out over this way. And we'll go, again, horizontal. And then if we think about where we're going in the negative x direction, well, we're just going to get steeper and steeper. So here I've pulled up a website where you can plot your slope field. So if you're doing the homework, you can check your work. And everything is going to be of the form that we had where we have dy dx, right, equals our function of x and y. And so you can put in the right-hand side right here, and you can change your the x-min and y-min and all that. And so basically the same thing that we had, except that they've plotted a lot more of the lines in a lot more, precision. So just like we did up above, we can use this direction field, the slope field, to sort of, show us what a solution looks like. So if we know we have one point on our solution, say our initial condition, then we know the direction that we're going. And it doesn't give us anything exact, but it does tell us something about the behavior. We know, especially, towards the edges. So we know that over here, our solution is diminishing down to nothing. And we know that it goes sort of off to infinity over here. So it does give us some behavior or some information about the behavior. Now, does that help us come up with a solution? Maybe it does. Let's look at the solutions that we have drawn on these two plots here. And this behavior really looks like exponential behavior, right? I mean, it's a guess. But we know that exponential functions start off really big, either positive or negative, and then get really small, or the opposite. They start off really small and they get really big. But this is like a negative exponential. So maybe our guess is that y of x, since we know that we're diminishing, it's got to be a negative exponential. So maybe e to the negative x. And let's put a couple constants in here because it must be like, let's see, we'll put a c out here and then a, I don't know what letter to use, k. C times e to the negative kx. And we can take another guess here. So like, what, does this work? Is this a solution to our equation, which remember is over here? So let's give it a try. Let's look at what dy dx would equal. It would be negative kc e to the negative kx, which equals, we've already got y to the x here, so negative k times y. So in order to make this fit into our differential equation, we just need k equal to 2. Okay, so then based on our guess, which was based on our differential field, we can find our solution. Y of x equals c times e to the negative 2x. And wow, this even helped us solve this equation. So we got pretty lucky, right? Because we had to guess. But in some cases, it is a start for getting a guess. And some differential equations are just so hard that you really have to rely on intuition and guessing to start getting you anywhere. So that's pretty much the gist of differential or of direction fields. In the homework, there's just a couple problems for you to plot some of these, and you can use a website like I have here. Just Google slope fields, or go to the URL that's written in there, and double check your work. But really, you just need to plot a couple of points and get a gist for the behavior of the solution. And that's pretty much it for chapter 1. We'll start chapter 2 in our next video.